I'll have to catch up with the recorded lecture.
Real quick, I have a question.
Go ahead.
Isn't the Super Bowl only once a year?
The Super Bowl is only once a year.
Then why do they have another one?
They only had one Super Bowl this year, and they'll only have one next year.
Okay, what I'm saying
So they
is
did
I
what they
thought
call
that-
the Pro Bowl.
I thought that the Super Bowl was in like November, fall.
No, that's when football gets kind of kicked off. It gets kicked off earlier than that.
But I'm so.
Oh, you're talking about the local Turkey Bowl?
No.
There's football on Thanksgiving, and that's a very normal thing. You watch
No,
football on Thanksgiving.
isn't the Super Bowl Sunday always in the fall?
No,
Later in the year? Why do we have another one?
it's always in February.
Dude, I swear. That's see? It
No, you're
is
thinking,
not
you're
February.
thinking of Thanksgiving, bro.
No, I'm not thinking of Thanksgiving.
Alright.
I know what I'm talking about.
Okay, lecture time. Let's get going with today's lecture. First, quick recap. What did we do last week? What was last week all about?
Sample spaces?
Probability functions, sample spaces, or our set of all possible outcomes. Let's just recap, going over a very common example, rolling 2 dice. Okay? Rolling 2 dice, we use an S to represent our set of all possible outcomes. If I roll 2 dice, what are all my possible outcomes?
36 plus 1.
Yeah, there's 36 of them. So I could roll a 1 and a 1. I could roll a 1 and a 2. I could roll a 1 and a 3, 1 and a 4, all the way up to I could roll a 6 and a 6.
Yep.
For a grand total of 36 possible outcomes. Now, assuming we have fair dice, regular dice, dice that you don't love, what is the probability of each outcome?
136.
So the probability of any outcome, little s just means one random thing out of big S. So little s could be that, little s could be that, little s could be anything in big S. So the probability of little s is 1 over 36, and we say for all little s in big S. So this was our set of possible outcomes. This was our probability function. What were our restrictions on the probability function? There were 2 restrictions.
All the probabilities of all the little s's have to add up to 1.
Yeah, the probability of all your outcomes has to add up to 1. So if it was just flipping a coin, I can't say the odds of flipping a heads is 50% and the odds of flipping a tail is 60%.
Yeah.
That doesn't make sense. The sum of your probabilities has to be 1 or 100% if you add up the possibility of each of your outcomes. Something has to happen. Okay, what was our other restriction? Our other restriction was the probability of a particular outcome has to be greater than or equal to 0. It doesn't make sense to have negative outcomes. I can't say, oh, the probability of flipping heads is equal to negative 50% and the probability of flipping tails is equal to 150%. And add them together and say, so there's a 100% chance you get one of the 2 outcomes.
Yeah.
Doesn't make sense. Okay, so those were our 2 restrictions on our probability function. And then our ordered pair, S together with P, is what we called our sample space. So your sample space is S and P, where S is your set of all possible outcomes, and P is your probability function. Okay, let's continue talking about when you're rolling 2 dice. Most game, when you're rolling 2 dice, what do you care about?
Their addition.
You care what the 2 dice add together to be, right? You're playing Monopoly or something, you roll something like a 7. So today, our next section is about events. And events are going to be capturing things like rolling a 7, rolling a 6, rolling a 5, things like that. So first, let's go over exactly what the definition of an event is, and then go over an example of an event in our scenario. Let's do the example first. Let's say that I want to talk about the event, you rolled a 7. Here's my sample space, here's S, here's P. What does it mean to roll a 7?
Means that the addition of the 2 dice add to 7.
Right, so being super explicit, that means that you rolled a 1 and a 6, or you rolled
A 2 and a 5.
2 and a 5, or you rolled,
3 and a 4.
or you rolled,
4 and a 3.
or you rolled,
5 and 2.
or you rolled.
6 and 1.
Now notice, all these things had to be in S. Right?
Yeah.
A is just now our collection, our event A, which we're calling rolling a 7. Our event A is a subset of S. We said in some sense there's a bunch of things in S that for our purposes are kind of the same thing. It's the same event. It's rolling a 7. And now, just using your own intuition, what's the probability of A?
It's 6 and 36, or 1/6.
He said it's 6 over 36. How on earth is he coming up with that number?
6 outcomes out of 36.
Right. What's the odds of getting this one? 1 in 36. This one. 1 in 36, 1 in 36, 1 in 36. Add them all up, that gives you the probability.
Pretty simple.
Pretty simple, pretty straightforward once you get your head behind what an event is. Okay, so now the exact definition is going to be precisely what we just did here. So let SP be a sample space, like we have one right here. Some sample space. Then, the set A as a subset of S is called an event. What's an event? It's any subset of S. Here's one particular event that we happen to care about that we call rolling a 7. And the probability of A, of that set, the probability of that event, is just equal to the sum for all little a and big A, sum up the probabilities of each of those little a's. So little a would be this thing. Here's one little a, here's another, here's another. Add them all up. That gives you the probability of some particular event A. How do you find the probability of some event A? You add up the probabilities of all the individual things inside big A. Exactly what we did, just more dense notation. Go ahead.
So we're allowing A here to also equal the entire set S in some cases?
A could be the entire set S. A could be nothing. Could be completely empty.
Okay.
Right? I could have my A be the event rolling a 13.
So the power set on S is also the set of all of the events on S? Would that be a proper way of...
You could say that, yes.
Okay.
But everyone else don't think about that way. Okay. So, that's the definition of an event. That's how you calculate the probability of an event. And we just barely did the example, rolling a 7 with 2 dice as an event. Good so far? Any questions so far? Okay, that's it for this whole section. Now we're just going to do a bunch of examples talking about events and calculating the probabilities. But that's the only new theory. We've covered it all. Almost. I guess there's this last little bit at the end. But now let's just do some more examples. Okay, so a new sample space. Let's say we're tossing a coin 5 times. Right? What is my S going to be?
Heads or tails? Or there's 5 of them, isn't there?
I'm flipping a coin 5 times. What is one possible outcome?
Heads.
I could have got heads, 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 heads all 5 times.
Oh, okay.
So here's one possible outcome. Heads, 2, 3, 4, 5. I could have gotten heads, 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 tails. I could have gotten heads, 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 tails, heads. All the way to tails, 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 tails. If you see my pattern, if not, who cares?
Yeah.
The point is, you see, it's all the possible outcomes.
Uh-huh.
Okay, question. How many things are in S? Let's scribble that up here. What is the size of S?
5 squared? Or is it 2 to the 5?
2 to the 5.
We've been counting strings for a long time now.
2 to the 5.
It's 2 to the 5.
2 to the 5 or 5 to the 2?
There's 2 possible choices for each.
There's just 10, right?
What?
I'm just throwing something random out there to make sure we're thinking.
There's 2 choices per element on the list.
Yeah. I'm flipping 5 times. 1, 2, 3, 4, 5. How many options do I have for my first coin flip? 2. And for each of those 2 outcomes, how many options do I have for my second one? 2. And for each of those 4 outcomes, how many options do I have for my third one? 2, 2, 2. So 2 times 2 times 2 times 2 times 2, or 2 to the 5, which is
32.
32.
Yeah. Thank you.
All right. Good so far? Now, the event A that we cared about, let's see, what were we on? A is the event, we only have 1 heads. So let's see, does this only have one heads? No, so that's not an A. Does this? No. Does this? No. None of the ones I have show up in A. What's an example of something in A? Heads, tails, 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 tails. There's one thing in A.
So there's just 5 things in A.
And then we could have tails, heads, tails, tails, tails. How did he get 5? I can choose to have the heads as my first flip, or the second, or the third, or the fourth, or the fifth. And if I were to write all those, then I would have written a total of 5 things. Maybe, probably should have just written all of them out. It's only a couple more. Okay, I only skipped 2. So the size of A is equal to?
5.
How many things were in A? 5. So now, what was the probability of me, if I flipped a coin 5 times, what is the odds that I only got a head once?
5 out of 32.
Just 5 out of 32. So you'll notice when you have a fair die or a fair coin or whatever, then your probability of A is typically going to be the size of A over the size of S. In our case, 5 over 32.
Why do you have to specify the fair part? Oh, because all the probabilities have to be the same.
Yeah, because all the probabilities have to be the same, which they typically will be. There'll be weird scenarios, jumping ahead, looking at like our spinner here, where that kind of thinking won't work.
Okay.
Okay, so there we go. Let's try another one. What about flipping 2 heads? What are the odds? You flip a coin 5 times, what are the odds that 2 of your coin flips turned out to be heads? So we're going to make now, there's nothing special about using A to symbolize an event, so I'll use B this time. So I'm going to let event B, we flip 2 heads. So what's an example of one thing in B? It could have been tails, heads, heads, tails, tails. And then there's all the other things in B. Not going to write them all out. B is you flipped heads twice. How many things are in B? 15. Keep in mind, how many possible outcomes are there?
There's 32.
32. 15 would mean like half of them have 2 heads. Does that sound right?
No. I feel like it would be less because you're taking up less space. That kind of makes sense. I don't know.
How can we think about this? I've got 5 coin flips. 2 of them are heads. I got 5 coin flips. We need to choose 2 of them to be heads.
2/5 of your total outcomes are 5 heads.
Add the 2 and the 5 in it.
5 choose 2.
2/5 of that you're going to have a hard time with.
Right.
Doesn't come out whole.
Doesn't come out whole.
5 choose 2. You got 5 options. Choose 2 of them to be heads. Here I got my 5 flips. 1, 2, 3, 4, 5. Now I got to choose 2 of them to be heads. Choose that one and choose that one, and now the rest have to be tails.
Right.
It's just 5 choose 2. Okay, and what is 5 choose 2? You guys remember how to calculate our chooses? You're going to need to for this section. Just without even thinking, what's the brute force way we do it? Maybe write the formula down here. Here's how you do n choose k in general. It's n factorial all over n minus k factorial times k factorial.
Yeah.
So in our case, it's 5 factorial all over n minus k. 5 minus 2 is 3, so 3 factorial, times whatever our k is, 2 factorial. Now what does that equal? Keep in mind, what is 5 factorial?
It's 120.
It's 5 times 4 times 3 times 2 times 1 by definition, right?
Yeah.
So I could rewrite this as 5 times 4 times 3 factorial. 5 times 4 times 3 times 2 times 1. Right?
Uh-huh.
All over, we're still over 3 factorial times 2 factorial. What do I have top and bottom? 3 factorial, so that cancels out with that. So 5 times 4 over 2 times 1. What's 2 times 1?
2.
That's great math. So we got 5 times 4 is
5 times 2.
5 times 4 is 20 divided by 2 is 10. Okay, there's 10, and that sure sounds good. Sounds like a reasonable answer.
So what was the third of them on?
So about a third of them have 2 heads.
Yeah, okay.
All right. Now let's calculate event C. Event C is going to be we have 3 heads.
But he was 5.
So something like heads, 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 tails, tails.
Isn't that just the same?
Isn't that just the same?
Oh, it is the same.
Yeah, this now is just going to be 5 choose 3.
But that's
5 choose 3 and 5 choose 2 give you the exact same thing. And so it's going to come out 10 again.
yeah, because you just, instead of just choosing 3 heads, you
So
choose 2 tails.
how many have no heads?
Or what?
1. That's just a flip. Tails, 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 tails.
Yeah.
So 1 with no heads. How many have 1 heads?
5.
5. How many have 2 heads? 10. How many have 3 heads? 10. How many have 4 heads? That means it only has 1 tails.
5.
So you could be, we're missing the heads in the first position, the second position, the third, the fourth.
Hey, this looks
And then finally, and you better add that up and it better come out to 32. We counted all the possible outcomes.
That also looks like a.
And that also looks like a row from our Fibonacci sequence.
No, our Pascal's right.
Yes. You can get the Fibonacci sequence from the Pascal's triangle.
Did he show us that?
Uh,
I don't remember.
we can come back to that. The two are very related to each other. I think I did at the time. Okay. But yes, I did mean Pascal's triangle.
Is that just a coincidence, or is there actually a relation there?
There's a relation there, and it's when I drew the triangles with the zeros and the ones.
I mean, for this problem specifically.
Oh, yes. The fact that that shows up, you might remember your binomial theorem. These are the coefficients to a binomial expansion. And yes, we will have a lot to say about that next week. But for now, just have fun with the fact that you can see it's there. Okay. So there we go. We calculated a few events, calculated the probabilities of a bunch of events. Any questions so far? So now you're learning how to calculate some basic probabilities. Getting ready to set up your little homemade casino. Start ripping off your friends and family. Right?
Yeah.
Okay. So let's move on to, we're now on rolling 10 dice. Okay. So here I've got a die. And I'm going to roll it 10 times. Or you can think about it as rolling 10 dice. Same thing. 1 die 10 times. Or rolling all 10 dice all in one go. First off, what does our sample space look like for rolling 10 dice? What's a natural one to use?
Unordered pair that has.
It's going to be S equal to,
Not ordered.
we could have the first die is a 1, the second die is a 1, the third die is a 1, the fourth die is a 1, the fifth die is a 1, 6th, 7th, 8th, 9th, 10th.
Unordered.
And we could go all the way up to ...
Six.
The first die is a 6, the second die is a 6,
Is it
3, 4,
or
5, 6, 7, 8, 9, 10. What a nightmare. Okay, only writing 2 things in there, but hopefully you understand what it is. Question, what's the size of S?
Very large.
Yes, the size of S is exactly very large, and that will get you full credit when that comes up on your test. Hi,
Good morning.
good morning. We got them all.
My word, that is so cool.
Yeah, back to back.
You must bring them cookies or something.
Not a single one.
No.
They just like you.
They just like the math.
They like the
Caleb rolls up
math. You
with
love the
his
math.
She's smiling so big.
I was so impressed with your handwriting. It's like, I want to take a picture of that and just look at it all day long. It's so good. Thank you.
Thank you. Okay.
It's 2 to the 10, right?
Huh?
Oh, no, it's 6 to 10.
How many options do we have for our first roll? How many options for the second?
6.
And the third, and the fourth, and the fifth, for a total of 6 times 6 times 6, 10 times, or 6 to the 10. Okay.
Every number.
So, humongous number. Whatever it is.
It's human.
Now, yeah, it should be able to hit 1 billion, but it should be over 1 million.
60,466,000.
All right, sounds good. So 60 million ballpark.
60 million.
Okay. Now, what is our probability of any particular roll?
1 in approximately 60 million.
Yeah, 1 in approximately 60 million. 1 over 6 to the 10.
Yeah.
So that's your odds of getting a 1 followed by a 1 followed by. It's just not going to happen.
That's pretty abysmal, yeah.
Yeah, pretty crazy. Once you do roll a dice 10 times, you do only get one of those outcomes, so think about it. The odds that you did that. It's crazy. Okay, so now what is our event going to be? Let's look at the event. You do not roll any ones. Oh, sorry, no. Let's look at the event. You roll at least 1 1.
Okay.
So let's look at the event. You roll at least 1 1. So what's something that could show up in here? Well, for one, we could have this show up in there. This has at least 1 1 in it.
Just ones and all twos.
This would not show up in there. Any rolls, series of rolls that has at least 1 1.
So there's at least 10.
So we could get 1, 2, 3, 1, 6, 4. How many numbers do I have? 6, 7, 8, 9, 10. Okay, here's one possible thing that could have showed up in here. Not gonna write them all out. All the series of rolls that have at least 1 1 show up in them.
Uh-huh.
How many? What is the size of A? How big is A?
Where did you get sevens from?
Oh, yeah.
I have no clue. All the things I chose to write. I just did 7s because they're easy to write. Okay, the rest are 2s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we're good. Thank you. Okay, here's one possible thing in A. We want all the rules that have at least 1 1. I give you a die. I give you 10 tries. You need to roll a 1 at least once. What are the odds you can do that?
Pretty likely.
Seems pretty likely. How many ways are there that we can get at least 1 1? Now, it turns out that's kind of a tricky thing to think of.
So why would you?
So what we often do is if you get stuck trying to figure out A, sometimes it's useful to instead think about A's complement.
Okay.
What would A's complement be in this scenario? Do you remember the complement?
Yeah.
The complement is everything not in A.
Don't you draw it with a dot? Like a little.
No.
I just really.
That's anything you can't. You don't.
You might be going all the way back to thinking about the, what's it called? The interior of a set.
Oh.
From topology,
Okay, sorry.
if that's what you're thinking of.
Yeah, that makes sense.
Okay, but no, the complement, everything that's not in A. So if A is you got at least 1 1, what is A's complement?
Everything that is not one.
You did not get any ones. Right? So A is absolutely no ones. So
Wait.
this could have something like a 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, there's one thing in A.
Just 5 to the 10.
Perfect.
5.
If you are a member of A's complement, let's see, there's 10 rules. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And my only restriction on you is you can't roll a 1. How many options are there for your first roll?
5.
5. How many options are there for your second roll? 5, 5, 5. And so 5 times 5 times 5, 10 times. And so the size of A complement is going to be equal to what?
5, 10.
5 to the 10. So now, what is the size of A?
1 to 10?
Just 1?
No, I get it right.
Definitely not right.
What?
How many total things are there in S?
6 to 10.
Minus 5.
How many? Perfect. So there's 6 to 10 things in S. 5 to the 10 of them have no ones. So how many of them have at least 1 1?
6 to 10 minus 5.
6 to 10 minus 5 to 10. Here's all our rules. Subtract away all the ones that don't have any ones, and what are you left with?
Big number.
All the ones that have at least 1 1.
Is there an easy way to calculate that?
Yeah,
Yeah, there.
right there. That's as beautiful as you can hope for.
Okay.
It's wonderful.
Fair enough. I won't shame it.
With me? So that's how you can calculate that. So now let's calculate the probability of these things. What is the probability of A complement?
A complement?
Yes.
It's 1 over 5 to 10.
What? 5 to 10 over 6 to
5 to the 10 over, it's the size of A complement over the size of S. This is typically the way you're going to do it when you have equal outcomes.
Yeah.
Which is going to be 5 to the 10 over 6 to the 10. Cancel out the 10s top and bottom and you're left with 5, 6, right?
Yeah. Wait, no.
No! You cannot just cancel out exponents. Otherwise, let me do some really tricky math for you. Let's do 1 to the 10 over 2 to the 10. Well, that's equal to 1/2, right?
No.
No, that's equal to 1 over 1024. This is not 1/2. Those are very different numbers.
Yes.
You can't just cancel out exponents.
Cancel that.
Okay. So it's 5 to the 10 over 6 to the 10. Or 5, 6 to the 10 is another way you can think about it. That's a valid thing to do with exponents. I can think about that as 5, 6 to the 10. And now if you were to go plug that into your calculator, you would get roughly 5, 6 to the 10, 16.2%, rounding to 3 decimal places. 16.2% chance. So there's a 16.2% chance that what?
You won't.
That you don't get any ones. So what is the probability now of A?
It's 100 minus that.
It's 100% minus that. Or in other words, it's
83.8.
wonderful. Someone not being lazy. Now we could have also calculated the probability of A directly. We could have said the probability of A is equal to the size of A, 6 to the 10 minus 5 to the 10, all over 6 to the 10. Split that up into two fractions. 6 to the 10 over 6 to the 10 is 1, minus 5 to the 10 over 6 to the 10.
That's just, oh,
It's going to give you the exact same thing.
Right.
So once again, that would come out to you, if you rounded it, 83.8%. So very likely that you're going to get at least 1-1. Set up a game that you could go rip off some people with. It's one I played before. You give someone a 6-sided die, and you tell them that they get 3 chances to try and roll a 6. If they roll the 6, you owe them $1. If they don't roll a 6, they owe you $1.
I remember you put this on a test one time.
You with me?
Uh-huh.
So, 6-sided die, you got 3 chances to roll. What are the odds in 3 tries that you get a 6? Most people think it's 1/6 chance on the first roll you get a 6, plus 1/6 chance on the second roll you get a 6, plus 1/6 chance on the third roll you get a 6.
It's 1/2.
So it's 50% chance that you roll a 6 in 3 tries.
No.
Is that correct?
Absolutely not.
Absolutely not. Let's go over how to calculate it. You got 3 chances, so now our sample space is just rolling a die 3 times. What's the event we care about? This time we'll call it B. B is, you get at least 1/6.
No, you get 3. Or, yeah, 1/6.
Yeah, so it could be something like first you rolled a 1, then you rolled a 2, then you rolled a 6. That's one valid outcome for B. You could have also gotten a 666. There's a valid outcome for B. If you roll a 6 at least one time, you win. Now what's the size of B? How many things are there in B?
6.
Well, that's kind of hard for us to think about. So we think about B complement. What is B complement? It's going to be, you don't have any 6s.
So it's 5 to 3.
So it's going to be like 1, 2, 3. There's one without any 6s.
Uh-huh.
So what is the size of B complement?
It's 5 to 3, right?
You roll the die 3 times, and you can't have any 6s. So how many options do you have for your first roll?
5.
5. How many options for your second?
7.
And 5. So the size of B here is 5 cubed.
And what's the size of our sample space?
What's the size of your sample space if you're rolling a die 3 times?
It's 6.
The size of S is just 6 cubed.
So it's the same. It's 6 cubed minus 5 cubed.
So the size of B is equal to 6 cubed minus 5 cubed.
Yeah.
All right, let's calculate the probability of B. What is the probability that you roll at least, or sorry,
Yeah.
let's do the probability of B complement. What is the probability that you don't roll any 6s?
5 cubed over 6 cubed.
5 cubed over 6 cubed. which is equal to roughly 58% if you round to 2 decimal places. So what is the probability that you do rule a 6?
42%.
Roughly 42%.
Really?
So they only have about a 42% chance of winning the game. And if you play it enough times,
You win.
you're going to collect money. Okay. Let's move on to another one. 4 of a kind in poker.
Sweet.
So what are the odds in poker that you get 4 of a kind? We talked about poker hands last time. How many poker hands are there?
It was 52 to choose 4. Is that right?
How many cards do you have in a poker hand?
You have 5 or 4?
5 cards.
5.
So, if we were to write out all the one possible poker hand, S would be something like, what could you have? You could have something like the ace of spades, followed by the 2 of hearts, followed by the 3 of clubs, together with, I don't know, the 4 of diamonds and the 5 of diamonds. Okay, there's one possible poker hand. And I actually should have written this as a set because it doesn't matter what order you have the cards in. It's not like flipping a coin where it matters which flip was first, which flip was second.
So that's okay.
Okay, but there's one potential poker hand.
And there's 52 possible.
How many possible poker hands are there? Well, first off, how many cards are in a deck?
52.
52. How many cards do you have in a poker hand?
5.
5. So, the size of S is just equal to 52 choose 5. Right?
Yeah.
Now, A is going to be the event. You have 4 of a kind. So it could have been something like you had the 2 of hearts, the 2 of clubs, the 2 of spades, the 2 of diamonds, and then you could have had some other random card. We'll say the 8 of hearts.
Okay.
There's one possible hand that gives you 4 of a kind. What is the size of A? How many possible poker hands give you 4 of a kind?
So you can have. There are 13 possible.
There's 13 possible types of 4 of a kind. You can have 4 of a kind on your aces, your 2s, your 3s, your 4s, dot, 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 all the way up to kings. Make sense so far?
Yeah.
So there's 13 ways that we can get our 4 of a kind, but now you have one remaining card. Once you have your 4 of a kind, how many ways are there to pick your remaining card?
48.
48. Because you took 4 cards out of the deck to get your 4 of a kind.
Right.
So you have a deck of 52, choose your 4 of a kind. There's 13 ways you can do that. Once you choose your 4 of a kind, you're left with 48 cards. So times 48. So these are all the possible ways you can get 4 of a kind. Here's all your possible poker hands. Here's how many of those are 4 of a kind. Let's calculate the probability now of A. What are the odds that you get dealt a hand that has 4 of a kind? Intuitively, you know that the odds of that are very small. Okay, so let's calculate it. It's going to be the size of A up here, 13 times 48, divided by 52 choose 5. What's 52 choose 5?
Very large.
That's going to be 52 factorial all over. What's 52 minus 5?
47.
47 factorial times 5 factorial. Here's our number, right?
Very small.
Okay, let's see what this is equal to. Keep in mind that this is our fraction line. How do you divide by a fraction? You multiply by the reciprocal, right? So I'm going to get 13 times 48 times 47 factorial times 5 factorial all over 52 factorial. With me so far? Now what is 52 factorial? That's 52 times 51 times 50 times 49 times 48, da da da, all the way down, right?
Yeah.
So I'm going to rewrite 52 factorial as 52 times 51 times 50 times 49 times 48 factorial. Not percent.
Cancels out with
Yeah, 48 times 47 factorial is
48 factorial.
48 factorial. There's 48 factorial, so that crosses out with this.
Yep.
So we've done that so far.
13 times 5 factorial is 100.
How many times is 13 going to 52?
It goes to 52.
4 times. So cross out the 13, cross out the 52, leaving us a 4 here. Let's see. 5 factorial, that's just 120. Maybe we'll really quick rewrite that as 120. So we have 120 all over 4 times 51 times 50 times 49. Right?
Yeah.
Take a 10 out of our 50 and a 10 out of our 120 here. So that leaves us a 5 on that one and a 12 on that. And then I can cancel out the 12 and the 4, leaving me 3.
Okay.
Cancel out the 4 with the 12, now leaving a 3, so we're left with 3 over
51 times 49 times 5.
51 times 5 times 49.
It's still pretty small.
Still pretty small, but now is something you can enter into your calculator. You can't go and enter this into your calculator. It's going to blow up.
It actually worked for me.
It did the canceling out for you?
It worked. It got me an answer. It was the right answer.
Because you could very quickly, you're going to run into a problem. If it's smart and cancels out for you, it can work. The problem you're going to run into is it's going to quickly start rounding off these numbers, representing them as a giant exponent.
Yeah.
And so, we got 3 divided by 51 times 5 times 49.
1 over 4,165.
Maybe, but it's 0.00024.
Yeah, that's the same.
So this comes out to 0.024%.
Quite low.
Very low probability that someone deals you 4 of a kind in a poker hand. And you can go calculate whatever poker hand you want and figure out its odds.
Looks like a royal flush.
What's a royal flush?
What's the rarest hand you can get is a better question.
A royal flush.
Royal flush.
Yeah.
Well, you know what the percentage on top of your head?
No. Okay. So now you can go calculate all the hands of poker that you care about. All right, with all that, let's ask a question. Jack and Jill, being Jack and Jill, they have 4 kids.
Okay.
We're on this one. What is more likely? That they have 2 kids of each gender, or 3 of one gender and 1 of the other? What's more likely? That you have a 50-50 split, or that you have 3 kids of one gender and 1 of the other?
So you don't feel the same likelihood. Can't be right.
Okay, let's set up our sample space. First off, what does our sample space look like? S, it's going to be all the way that Jack and Jill can have 4 kids.
Yeah.
They could have had
Oh, it is more likely.
boy, 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 boy. They could have had boy, 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 girl. All the way down to girl, 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 girl. Right? What is the size of S? How many possible outcomes are there?
There is 2 to the 4.
2 to the 4. How many options for the first kid? 2 for the second, 2 for the third, 2 for the fourth, 2. 2 times 2 times 2 times 2 is 16. Okay. We said A is, we'll make A the event that they have the same number of boys and girls.
Okay.
So A could be, one thing in there would be boy, boy, girl, girl. Here's one thing in A.
Does it matter the order in this case?
No, we just care that they have 2 boys, 2 girls. I mean, the order matters because those are different events. Having a boy, boy, girl, girl is a different event than having a girl, girl, boy, boy. Or sorry, those are different outcomes. So those would both show up in here. Okay, what's the size of A? Sorry, that's not the size of A, that's just A. What is the size of A?
A
How can we think about this? You're having how many kids?
4,
How many are going to be, you can pick boy or girl, how many are going to be boys?
2.
2, so you got 4. Of those 4, you got to choose 2 of them to be boys. So the answer is 4 choose 2, which is equal to 4 factorial over 2 factorial over 2 times 2 factorial, 4 factorial over 2 factorial times 2 factorial. You got to get to the point where you can start doing stuff like this in your head. A 2 factorial cancels out with the 2 factorial up there, leaving in the top we have 4 times 3 over 2 factorial. 4 times 3 is 12 divided by 2 is 6. Okay, so what is the probability of A? What is the odds if you go and you have 4 kids that you have 2 boys and 2 girls?
16 over 6.
6 over 16.
Oh, sorry.
Can't be over 100%.
6
So 6 over 16 or 3/8 is another way we can write it. I'll keep the 6 over 16. Helps keep it clear where we come from. Or 6 divided by 16 is equal to 37.5%. Just give you a percent on it. Okay, now we'll make event B is going to be that you have the same amount of boys and girls, or sorry, is a 3-1 split.
Right.
So B could have something in it like boy, 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 girl. Oops, boy, 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 girl. But it could also have girl, girl, boy, boy, boy. Right? It's just a 3-1 split.
And those are not the same thing.
Those are 2 different things.
Okay.
We're just wondering, is it more likely that you'd have a 50-50 split between your kids, or that you have 3 of one gender and 1 of the other? What's more likely?
The 50-50 seems like it's more likely.
The 50-50 seems like it's more likely, but let's not rely on intuition. Let's
Figure it out.
do some math. All right, so what is the size of B?
4 choose 3 or 4 choose
4 choose 1 or 4 choose
4 choose 1 or 4 choose 3, which is it?
3. They're the same.
Oh, so it's just one of them?
Or both of them.
It's going to be both of them. 4 choose 3 are the amount of ways you could have, if we think about, we'll count the number of boys. Have 4 kids, I can have 3 of them are boys, or 4 kids and 1 of them are boys. Because you got to count both.
Those aren't.
These are all the ways that you have 3 boys and 1 girl. These are all the ways that you have 3 girls and 1 boy. So these are all the ways you can have a 3-1 split.
Yeah. Okay.
And now, what is 4 choose 1?
4.
4. If I've got 4 objects in a bag, and you get to choose 1, how many possible ways can you do it? 4. And 4 choose 3 is the exact same thing as 4 choose 1. Because if you choose 3 things, that's the same as choosing 1 to leave behind.
Right.
So there's 8.
So there's 8. So 8 out of 16, or in other words, 50%. Probability of B is 50%. And so you are more likely to have a 3-1 split than you are to have 50-50.
That makes no sense.
You're more likely to have 2 boys and 2 girls than you are to have 3 boys and 1 girl.
But you're more likely to get 3 overall.
But you're more likely to have 3 of one gender and 1 of the other than you are to have exactly a 50-50 split.
That's so weird. That makes sense though. It's like you have. It's like you're choosing out of one.
Let's just do this right off the top of our heads. What are the odds that you have 3 boy and 1 girl?
That's 1 in.
Huh?
1 in 16.
Oh, sorry, not boy, 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 girl, but that in all the ways you do it, 3 of your kids turned out to be boys, 1 turned out to be a girl. What are the odds of that?
Oh. So you can remove.
You had 4 kids. What are the odds that only 1 of them is a girl?
4 choose.
4 choose 1.
4 choose 1, or in other words,
4.
as a percentage, it's
1/4.
4 out of 16 is
25%.
25%. So 25% chance that you have 3 boys and 1 girl, 25% chance that you have 3 girls and 1 boy. 37.5% chance that you have 2 of each.
But why is that not? Oh, because you can have the all 4.
But we were adding both those together. We were saying 3 of one gender and 1 of the other.
Right.
So, you are more likely to have 3 kids of one gender and 1 of the other than you are to have a 50-50 split.
Does like the census back that up?
I'm sure that if you go collect enough data, this is the way it comes out. That would be beyond shocking. I'm sure everyone would be talking about it if this did not come out this way. Because this is just simple math.
That's wild.
Unintuitive. I don't know about wild, but
So unintuitive.
once you think about it for a second, it starts to make sense.
And does that, do the percentages change at all when you scale up the amount of kids you have?
You can go play with it real quick. See how it comes out for different numbers. Not sure exactly what you're saying it is that you care about, but
I'm saying as you increase the amount of kids you have, does
you're still comparing what? Then so if we're talking about 5 kids, you're comparing a 4-1 split with.
I don't know.
But now you can't split 5 down the middle, so we gotta jump to 6. So depends on what exactly you mean. Okay. But there we go. There's a boy-girl one. Okay. Now let's do the birthday problem. Everyone loves their birthday, right? Let's see. There's 6 of you in this class. When's your birthday?
June 24th.
When's your birthday?
May 19th.
When's your birthday?
January 7th.
When's your birthday?
October 12th.
When's your birthday?
October 12th.
What? It happened? When's your birthday?
September 26th.
September 26th. Okay. We had 6 people in this room. 2 of you had the same birthday. What are the odds of that?
Pretty low.
Is that pretty low or is that pretty high? Was that to be expected?
Well, I mean, I share a birthday with
How many days are there in a year?
365.
Oh, good job. Okay. 2 of them have the same birthday. That was shocking. How shocking is that?
That's not very shocking.
Not very shocking, kind of shocking, really shocking. I wasn't expecting it.
I share a birthday with people.
So let's calculate the odds. Well, yeah. If you know at least 365 people, you share a birthday with one of them. Or odds are.
Not necessarily.
Yeah, should have said that a bit different. Get 366 people together in a room, guaranteed at least 2 of them share a birthday. Odds are much more than that share a birthday, but there's only so many days. Okay, so let's run through the birthday problem, and let's calculate the probability that that turned out to be the case.
Sweet.
You with me? Now, what is S going to be? S, our sample space.
All the days in a year.
All the possible birthdays that we could have for 6 people.
Are we counting years or just days?
Just birthdays.
Okay.
Right? You know what it means to have the same birthday. So, only 365 options. We're not going to count leap years. So, what is the size of S here?
365.
I don't want to write out an example of S writing out 6 birthdays.
It's pretty easy.
But the size of S, so we have 6 people in the room. 1, 2, 3, 4, 5, 6. How many options were there for her birthday?
365.
And for hers? And for yours? And for his? And for his? And for hers?
That's a huge number.
So the size of S is 365 to the 6.
That's massive.
That is massive. There is a bunch of different ways that we could have had all your birthdays.
That is insane.
Right?
Yeah.
Okay. Now, what did we care about?
The same.
Our event A is to have the same birthday. Now that's kind of hard to think about.
So what do you think about the ones that don't have the same birthday?
So let's think about a complement. None of them have the same birthday. So, starting with her, how many options were there for her birthday?
365.
365.
Oh, it's just 365.
And now, if she can't have the same birthday as hers, how many options for her birthday?
364.
364. And then if yours can't be the same as either of theirs, then
363.
363, 362, 361, 360.
Oh, yeah. Just
So what is the probability now of a complement?
365.
What are the odds that all you guys don't have the same birthday? That none of you share a birthday?
365 factorial over 365 to the 6.
Not factorial.
Is that not factorial? Oh, no. It's 365 to 6, sorry.
So the probability now of a complement is equal to
No.
365 times 364
It's just
times 363
you have notation.
times 362 times 361 times 360 all over the size of S, which is 365 to the 6, right?
Yeah.
Now I'm going to manually write this out. 365 times 365 times 365 times 365 times 365 times 365. You with me?
Yeah, that counts though.
Now notice that 365 over 365 is 1. 364 over 365 is
Very close to 1.
really close to 1. 363 over 365 is really close to 1. And really close to 1, really close to 1, really close to 1. And we take a bunch of numbers really close to 1 and you multiply them together,
You get almost 1.
and it's kind of expected in this account that we would expect it to come out close to 1. Let's see what it actually comes out to, but we expect it to be a very high chance that two people didn't have the same birthday.
Right. Can your calculator do this?
I don't know if there's an easy way to enter that notation. So 365 times 364 times 363 times 362 times 361 times 360, all divided by 365 to the 6. And it comes out to 96%.
What's that?
It's pretty high.
Pretty high, yes.
So there was a 96% chance that two of you didn't share the same birthday. And there was only a 4% chance that two of you did share the same birthday. And so it was unlikely that it happened,
4% unlikely.
right?
Yeah.
Now, let's just think about it for a somewhat bigger number. Let's say there could have been 23 people in the class, right? And we redid all this. What do you think the odds come out to now with 23 people? Just throw out a number. I know that you're just kind of spitball guessing.
Close to 80 probably.
Probably about 80% for 23 people.
Yeah.
75% about.
You're going to say 75? Come on. Give me a number, any number.
78.
78%. Oh,
I like 75.
you like 75? You like your iPad?
2.
No number? All right. And the odds with 23 people would come out close to 50%.
Really?
And if you go and you take the time to calculate. Because every time you add on another one, the number is getting smaller and smaller and smaller. And so it starts having more and more of an effect.
Oh.
So this is a common, what would you call it? I'll call it a magic trick. That, some pretend sidekick does on stage. They're in a big auditorium. You got a row that has like 50 people on it. You say, I'm sensing on the second row here, 2 people share the same birthday. And you have them read out their birthdays, and more likely than not, 2 of them have the same birthday.
So awkward if it wasn't.
And then if it wasn't, you can say, oh,
I must have sensed the wrong row. Maybe it was the first row.
Just go through the whole lot.
Once you get through enough people, you're guaranteed, right?
Yeah, always gets 366.
Not per row, necessarily.
Guaranteed in terms of the odds.
Right.
So, common trick. There you go. Called the birthday problem. And if it's more than 23 people, don't be impressed. Right?
Yeah, I share a birthday with 2 people in my class.
We could be more impressed with what happened here, right? 4%. 4% events, they happen. Teach this class enough times, I was bound to finally get one where it happened. And it happened now, finally.
That's cool.
Okay. So that's the birthday problem. Our last little bit of theory for the section now is a quick proof. What are we going to prove? We are going to prove that what?
that your mom has more mass than the sun.
Your mom has more mass than the sun? Allow 2 to equal 1. I can prove it for you. Alright, so A intersect B plus the probability of A union B. Alright, here's what we're going to prove. Pick two events, any two events, A and B. Then the probability of A plus the probability of B is equal to the probability of A intersect B plus the probability of A union B.
This is in the same sample space?
Yeah, same sample space. A and B are both events in some sample space.
Okay.
Now, here's something that we've already proven in the past, which just smells a lot like. The size of A plus the size of B is equal to the size of A union B plus the size of A intersect B. And we can really quick see that with just a picture again, really quick. Here's some set A, here's some set B. If we do A plus B, A is everything in A, B is everything in B. You count that intersection twice. So if you do all of A plus all of B,
You have to minus the
then you did that and that. If you want to get just A union B, you need to subtract the intersection. So if you subtract now the intersection, then you're left with just A union B.
Are we assuming?
Move that to the other side, and that gives you this equation.
I guess we know that the intersection.
We're not going to use this formula to prove it.
Uh,
I just want you to see how similar it already is.
but the intersection of A and B is an event in the sample space?
Sure, remember, the union of any two events is just a new event, and the intersection of any two events is just an event. What the set intersected with the set?
So shot.
Another set. Is that other set still going to be a subset of S?
Yes.
Then it's an event.
Okay.
And you can phrase these types of events if you want. I could say A is the event, rule of 7. And I could have said B is the event, rolled an odd. And I could ask the question now, what are the odds that you rolled a 7 and an odd? That would be the intersection of those. And I could say, what are the odds that you rolled a 7 or an odd? And that would be these.
How does that really make sense though? I don't know. Anyways.
Hold on, let's make sure that that makes sense. So let's say that S is our sample space for rolling two dice. What would A look like, roughly?
All the
A is going to be you rolled a 7.
Right.
So A is going to be something like a 6 and 1, all the way down to 1 and a 6.
Yeah, what was it? It was like 6 out of 36 or something?
And the size of A is going to be 6. 6 ways you can roll 7. B now, we'll say, is you just rolled an odd number. So you could have rolled a 3 or a 5 or a 7 or a 9 or an 11.
Right.
So you could have rolled something like a 2, 1.
With two dice, isn't it more likely to roll an even than an odd?
Now, it's the exact same both ways.
Yeah.
Let's make that make sense really quick. With your first die and your second die, how many options are there for what goes here?
6.
Here's what you could have rolled. You could have rolled an even and an even. You could have rolled an even and an odd. You could have rolled an odd and an even. You could have rolled an odd and an odd. Both these, when you add together, give you an odd. Both these, when you add together, give you an even.
There's just, I was just wondering that because there's more evens than odds if you add the two numbers.
There are, but your highest probability is your 7.
That's so cool.
And your 12 and your 2 are your lowest probability.
Weird.
Okay, anyways, so you could roll a 2 and a 1. You could roll, obviously, a 6 and a 1. You could have rolled a 6 and a 5. Dot, dot, dot. What's the size of B here? Half your rules
Yeah.
are going to be an odd.
What's happening? Yeah. 18.
Yes. Okay,
Sorry.
so now what are the odds that you rolled a 7 and an odd? So that would be the probability. A 7 and an odd means A intersected with B. You did both. Well, in this case, A intersected with B, I kind of picked a stupid example. A intersected with B is just the same thing as A.
It is.
Yeah,
Oh, yeah.
rolls.
Yeah. So that is going to just be now 1/6.
But the.
Now if I said the probability that you rolled a 7 or you rolled an odd,
Is this the probability?
well, in this case, once again, it's a dumb question. Since A is a subset of B, then that's also just the probability of B. And so that's just going to be 1/2. Let's say C was you rolled an even and make this a little bit more interesting. C is you rolled an even, so you could have rolled a 1 and a 1, all the way down to a 6 and a 6, right? What's the size of C? How many ways can you roll an even number?
It's also the same as
Once again, 18. Now let's ask these questions. What's the probability of A intersect C? What's the odds that you rolled a 7 and an even?
0.
0. So in that case, it comes out to just 0 because our intersection is empty. More interesting now, what's the probability of A union C?
100%.
That you rolled a 7 or you rolled an even.
Sorry.
How many ways can you roll 7?
6 times.
How many ways can you roll an even?
18 times. And they have nothing.
They have nothing in common, so what's the union of these two sets?
It's 6 plus 18, so 20.
24. So this is going to be 24 over 36, or in other words, it's going to be equal to,
1/3. Or 2/3.
what cancels out top and bottom? So 6, 4, yeah, 2/3. With the 12. So 66% chance. Okay, so there we go, giving you some quick examples of how these probabilities might show up. Okay, so here's what we're proving once again. And now let's just kind of show how we've been doing this in our simple case. If we know the size of S, then we've been saying what's the probability of A.
It's the size of A over the size of S.
Yeah, when you have these normal distributions, not normal distributions, when you have these equally likely outcomes, then this, in all our cases so far, now it doesn't have to be, but so far in all our cases, probability of A has just been the size of A over the size of S. The probability of B has been the size of B over the size of S. The probability of this would just be the size of A intersect B over the size of S. And then the probability of this would just be the size of A union B over the size of S. Multiply both sides by the size of S, and you're left with this formula, which we've already proven. Now, that's in the case where all outcomes happen to be equally likely, which we're not guaranteed. So now let's actually just prove it in general, but most of the time, that's the math you're doing in these problems that we're giving you. So I wanted to show that special case. Okay. So, let SP be a sample space with events A and B. Okay, we want to show that this is equal to this, right? The way that I'm going to do this is I'm going to show that for any little s and big S you choose, it shows up on both sides of this equation the same number of times.
Okay.
So 2. Let little s in maybe write out explicitly what that formula means. So maybe just write that one time. So then, probability of A plus probability of B equaling the probability of A intersect the probability of B plus the probability of A union the probability of B means, what does that equation mean? It means that the sum for all little a in big A of P of A plus the sum for all little b in big B of P of B. Maybe I'll just use little s for our variable that we're plugging in here. Just a dummy variable, doesn't matter what we call it, but I think it'll help keep what I'm saying the most clear.
Is it the same for both events though?
Well, all we know about this set A and this set B is that they're subsets of big S, whatever that is.
Right.
So we'll say little s is a random element in big S. And so for all the elements of big S that show up in A is one way you can think about that.
Okay.
Of S plus, for all little s and b, its probability would be equal to
It should be A and B for your, shouldn't it?
the sum for all little s in A union B of its probability
Oh, no, you're right.
plus the sum for all little s in A intersect B of its probability.
Yep.
Okay, 3. So now, let little s in big S pick anything out of big S you want. And observe there are 4 outcomes, 4 possible outcomes. So, 1, we could have S is not in A and S is not in B. If S is not in A and S is not in B, how many times does the probability of little s show up on this side of the equation? It wasn't in A, so it doesn't show up here. It wasn't in B, so it doesn't show up here.
0.
If it wasn't in either A or B, does it show up in A union B? No. And will it show up in your intersection? No.
So it's 0.
So if it's in that and that, S,
P of S.
yeah, you can say it that way too if you want. P of S doesn't show.
Or just say it's equal to 0.
Well, we'll just say it doesn't show. Okay, what is our second possible case?
That S is in A and not B.
If S is in A and S is not in B, how many times does it show up on this side of the equation?
Half.
It shows up here
Or once, yeah, sorry.
and doesn't show up there. Does it show up here? Does it show up here? Now, that gives P of S shows once on both sides. Okay, what's our third scenario?
It's in B and not A.
So we could do
Isn't that the same as the second one? though?
S is not in A and S is in B. What would that mean? Doesn't show up here, does show up here, does show up here, doesn't show up there. So once again, that gives exactly what we wrote up here. P of S shows up once on both sides.
Okay.
Now our final scenario is what?
They show them both.
Yeah. If S is in A and S is in B, then it shows up here, it shows up here, it shows up here, and it shows up here. It shows up on both sides of the expression, the equation, twice. P of S shows twice on both sides. 4. Therefore, both sides of the equation add the exact same terms. Both sides add the same terms. And so are equal. Right? I just barely showed, because they have to be adding ultimately elements from big S. So grab any element from big S you want. No matter which one you grab, it shows up on both sides of this equation the same number of times. Or at least its probability does.
Right.
And so if you're always adding the same terms to both sides of the equation the same number of times, you're keeping your equation equal. Okay.
Is
So
that how they do the proof of both too?
it's going to be some sort of counting proof like that.
Interesting.
It's going to be the only real way to do it. So it's going to have the same basic idea. Grab any small s out of big S, shows up on both sides of this equation the same number of times. It's definitely going to have that flow. Okay, let's notice some properties now really quick. So we just barely proved this equation right here. Now we're just going to look at some quick consequences of that equation. What happens if A and B are events that have nothing in common? Or in other words, if A and B, what happens if their intersection is empty? Then what is the probability of their intersection? 0. And so you're just left with this.
Right.
That's what this first thing is going to say. If A intersect B is the empty set, then the probability of A plus the probability of B is just equal to the probability of their union.
Okay.
Now, in general, the probability of A intersect B, the smallest it could possibly be is
A or B.
the smallest that the probability of A intersect B could possibly be is 0. You can't get a negative probability.
Oh, yeah.
Or it could be some positive number. So it's either some positive number or it's 0. If it's 0 and I subtract it from this side, that doesn't change the equation.
Okay.
If it's not 0 and I subtract it from this side, I now make this side smaller than this side.
So it's less than.
So the probability of A union B is always going to be less than or equal to the probability of A plus probability of B.
Got it.
Equal to when the two sets have no elements in common, otherwise less than. And so that's all this is saying. Probability of A union B is always less than or equal to the probability of A plus probability of B. And it's only equal in the case
Got it.
where
The intersection is 0.
the probability of the intersection is 0.
Which is the same thing as the intersection is 0. Right.
No. The intersection could have an outcome in there, and the probability of that outcome could be 0.
Oh, okay.
Because we allow in our sample space the probability of the outcome to be 0. We've just been working in scenarios where we said the probability of each outcome is equally likely, so it was never 0. But that could happen. Okay. What is the probability of all of S? What's my event? I say, what are the odds that when you roll 2 dice, you roll one of the possible 36 outcomes?
100%.
100%. The probability of S is always and forever 100%. And then finally, what's the probability of the empty set?
How does that make sense to add?
Is the empty set an event?
It's a subset of S, I guess.
It's a subset of S, so it's an event.
But it has no.
So what's the probability?
But it
Nothing
has,
happening, 0.
So it gives you the empty sum. And what is the empty sum equal to? 0. The empty sum is 0. The empty product is 1. And then finally, the probability of A complement is 1 minus the probability of A. We've already used that thinking a few times.
yeah, that makes sense.
If I tell you that I rigged some coins, that the probability of rolling heads is 60, or flipping heads is 60%, what's the probability of flipping not heads or tails? 40%. And this is the way you calculated it. Okay. So that ends our first section.
Maybe.
On to the second section.
Can we have a small break before?
Let's go ahead and take a break.
Feels like my brain, like the eye's like halfway through.
All right. Continuing with our lecture today, we're moving to, I wrote that funny, conditional probability and independence. There isn't a notion of independent probability. I don't know why I wrote that way. Conditional probability and then events being independent of each other. Okay, so let's once again prime your intuition with a little bit of an example, just making up some numbers for me. What are the odds that a student is late for school? You know, take some random student, you know, a decently good student. Yeah, no, none of you guys. Okay, what are the odds that they're late for school?
30%.
Well, that's pretty high. Let's say, you know, pretty decent kids, there's like a 10% chance that they're going to be late for school on a given day.
Did you see the devotional this morning?
No, I did not. Okay.
Yeah, I was on time today, guys.
Now next, what are the odds that a student's alarm clock breaks, doesn't work, doesn't go off for whatever reason?
Very low.
80%.
We'll put that down at, you know, another like 5%, whatever.
Okay.
Accidentally unplug the clock, whatever is going on. Now, what are the odds that a student is late for school given their alarm clock broke?
100%.
Well, now it's not 100%, but now you see how that suddenly makes the odds of them being late probably closer to like 95% or whatever. Just making up numbers, giving you intuition.
Okay.
So, here was the odds of the event. Knowing some other event occurred can drastically change the odds of that event occurring.
That seems like calculus.
Well, it's just conditional probability. So what are now the odds given that some other event occurred? So initially it's 10% that you're going to be late. Now I say, well, it's now known that this 5% event occurred and their alarm clock broke. So I say, what's the odds that Jeffrey's going to be late? You say, 10% chance. I say, I know for a fact that his alarm clock broke.
You say 95.
Then you might say, okay, that changes my answer now. I'm going to say it's more like a 95% chance that he's being late.
So is that
This is what we call conditional probability, giving you intuition for it. What would it mean for there to be independent events? That would be when it doesn't change it.
right?
I say, what are the odds? I'm going to flip a coin 5 times. What are the odds that my second toss is heads?
You say 50%.
50%. I say, what if my first flip was tails though? Now what are the odds that my second flip is heads?
50%.
50% doesn't change it. Those are independent events. So independent events where knowing one event occurred doesn't change the odds of the other event occurring. Right? I say, what's the odds that Jeffrey's late? You say 10%. I say, well, I know for a fact that his mom packed him a peanut butter sandwich. How does that change?
It doesn't.
It doesn't. Those would be independent events. You wouldn't expect those to be any way related.
Right.
So that's roughly what we mean by events being independent. And conditional probability is now calculating the probability given some condition, knowing some event occurred. Okay. So let's do a bit more concrete now with some actual numbers we can calculate. Once again, we're just rolling 2 dice, same way we know in love, same sample space we know in love. We're going to make A is the event, I rolled an 8. B is the event, I rolled an even. Let's calculate the probabilities. First off, what are the odds of me rolling an 8?
36.
What is it?
Is it 5 out of 36?
5 out of 36. You guys know how to do this off the top of your head yet? Did I already show you the square? Saw the square? How many ways are there to rule 8? You can have a 6 and a 2, a 5 and a 3, a 4 and a 4, a 3 and a 5, a 2 and a 6.
Yeah.
Okay, there's 5. So 5 out of 36 for rolling an 8. How many ways can you roll an even with 2 dice?
Half of 36.
Half of 36, which is
18.
18. So there's 18 ways to roll an even. And there's 5 ways to roll an 8. Good so far?
Sure, yeah.
Okay. Now, I take my dice and I roll them. I don't let you see. I say, what are the odds I rolled an 8? But I'm going to give you a hint. I for sure rolled an even. Now, what are the odds that I rolled an 8?
Ooh.
If I for sure rolled an even, then you now know I rolled one of these 18 rolls.
Okay, so it's 5 out of 18, right?
So there's 18 possible ways I can roll an even. I'm asking you, what are the odds I rolled an 8? 5 of those 18 rolls are going to be
8.
8. Am I losing any of you on this?
No, that makes sense to me.
So here's how you read this. What is the probability of A given B? Is the way that you read that. What is the probability event A occurred given event B occurred? What's the probability I rolled an 8 given I rolled an even? So you know I rolled an even. What are the probabilities that my roll was an 8?
But if you know you rolled an even.
Then it had to be one of those 18 rolls. You know that I either rolled a 2, a 4, a 6, an 8, a 10, or a 12.
6.
There's 18 ways I could have done all those. 5/18 of those correspond with me rolling an 8.
Right.
With me so far? When I say rolling an even, I don't mean one of the dice is showing an even. I mean when you add them together, it comes out even. Okay. Alright. Now let's try another one. Here I take the die. I say, what do you think the odds are I rolled an even, given I rolled an 8?
100%. Actually, yeah, 10%.
So I tell you I rolled an 8. Now what are the odds I rolled an even? 100%. So now notice something very important. The probability of A given B is very, very, very different from the probability of B given A.
It's pretty evident.
Good?
Yeah.
Now that we've primed our intuition some, let's go through the actual definition and how to just calculate these rather than having to carefully think it through every time. So let A and B be events in some sample space SP, where the probability of event B is not 0. Because we're going to say that B happened. Well, we're going to say the probability of A given B happened. If B happened, its probability can't be 0, otherwise it doesn't make sense.
Right.
So then the probability of A given B, here's how you calculate it. It's the probability of A intersect B over the probability of B.
Okay.
Now let's make this make sense.
Oh, that makes sense.
Here's our picture. Here's S. A are all these events. B are all these events.
Okay.
Now if I first ask you, what's the probability of A, assuming all events are equally likely, that's like what portion of the area here is A? Right? And up here, I don't know, probably comes out to about 1/7, whatever.
Right.
But now, if I'm asking you, what is the probability of A given B happened? If I say given B, now this is we know that it's somewhere in B. And so the question is, what portion of B does A cover? And that's the portion I have striped in here. The portion of A that B covers is exactly what A intersect B is. So it's the portion of B that A covers divided by B. And that's the probability of getting that shaded in space there. Is that connecting with your intuition? And so now looking at this case, it would be something more like, I don't know what that is, probably like 5/8 or whatever.
Yeah.
Make sense? So there's the visualization to try and help it click. Okay, let's set it up with a completely different problem and once again do our calculation. We'll say A is I spun a 1. And we'll say B is an odd. And you could write those out for the sample space here. I'm just going to use words rather than writing everything explicitly.
And we're looking at the probability of the 1.
So first off, let's look at the probability that I spin a 1 on the spinner. So here's my spinner. We found out in nature, right? It was in the Arctic, I think. And we give it a good spin.
It's solid.
What are the odds that we land on 1?
1/2.
About 1/2, right?
Yeah.
So I hide my spinner and I spin it. And I say, what are the odds that I spun a 1? You say 50%. Okay. Now once again, I hide my spinner, I spin it. I say, what are the odds I spun a 1? But this time I'm going to tell you I for sure spun an odd. If I for sure spun an odd, I either spun a 1 or a 3.
So 5/8 of them.
So 5/8 of my area is an odd. So now the probability of A given B, is going to be equal to, just brute forcing it out, probability of A intersect B all over the probability of B. What is the probability of A intersect B? What was A?
1.
I spun a 1. What was B?
I got an odd.
A 1 or a 3. What's the intersection of 1 and 1 and 3?
1.
Just 1, so that's just probability of 1. So upstairs, this is just 1/2. Downstairs, what's the probability of B? What's the probability I got a 1 or a 3?
5/8.
5/8. So 1/2 over 5/8.
So it's 10.
Flip the reciprocal. So it's going to be 1/2 times 8/5, which is equal to
8/10 or 4/5.
4/5.
Okay.
Now the other way you could have just saw that, thinking through it. If you know it landed on an odd, odds account for 5/8 of the whole circle, and 4/8 of those correspond to a 1. So 4/8 over 5/8 or 4 over 5, 1. So trying to give you one that you could easily just reason through thinking about it, as well as showing you the formula, plugging in, getting the answer.
All right.
Good? All right, let's play another game. This time we're tossing a coin. I'm tossing a coin 5 times. What are the odds that my first flip was a heads, given that my last flip was a tails?
It's the same, 50%.
So here I take 5 coins, I flip them all out. First, second, third, fourth, fifth. So I got my 5 coins lined out. I say, what's the odds that my first flip was a heads? You say 50%. I say, what if I tell you that my last flip was for sure a tails? Now what's the odds that my first flip was a heads? doesn't change anything. It's still just 50% or 1/2. So those are independent events. On the other hand, I say, what are the odds that my first flip was a heads? You say 50%. I say, well, there were exactly 3 tails.
It's still gotta be 50%.
Now what are the odds that my first flip was a heads?
It can, there's no.
If there's exactly 3 tails.
Doesn't change.
Does it change?
No, it can't. Surely.
Well, let's help your intuition here. What if I told you I have 5 tails? Now what's the odds that my first flip was a heads? 0. That changed it. Why does knowing 3 tails not change it? Maybe it does change it. And in fact, it does change it. So let's think this through. If I told you that I had 3 tails, what must my flips look like?
Heads, tails, or something.
So we'll say B is 3 tails. What is the size of B equal to? How many of my flips have exactly 3 tails in them?
We did this before.
5, yeah. 5 choose 3.
5 choose 3. I've got 5 flips. Choose 3 of them to be tails. 5 choose 3. Or in other words, what's that equal to?
I choose 2.
Which is equal to, I want the number now. Come on, you guys. These are getting to the point you can do them in your head. 5 factorial over 3 factorial times 2 factorial is
10, wasn't
just
it?
10.
Oh, yeah.
I hope you're not remembering and you just
I
rethought
know,
it through.
Went through 10, but
You're doing 5 times 4 divided by 2, essentially. Okay, 10. Of those, how many have a heads in the first position?
Half? No.
It's going to be half of them. Or in other words, you know I got 3 heads or 2 tails, 3 tails and 2 heads. What are the odds that my first one was a heads then?
50%.
I've got a bag of 2 heads and 3 tails. I got to choose one to go first. Where are the odds I pick a heads?
Yeah. 10 choose 1.
Just 2 fifths.
Oh.
2 fifths of my 10 outcomes here are going to start with a head. Because I have 3 tails, so I only have 2 heads.
Okay.
I pick 3 boys and 2 girls, have you all come up here, and I put you in a random order. What are the odds I put a girl first? If I got 3 boys and 2 girls, 2 fifths. I got 3 tails, 2 heads. What are the odds a heads came first? It's now 2 fifths. So the answer there is now 2 fifths. Or if we would have written out all the possible ways we could do it, you find out that there's 4 of them. 4 over 10 would have given you 2 fifths. Looking at the size of the sets, if you wanted to draw them all out. Okay, so that time it was dependent upon. You were given some actual information that changed the odds that your first flip was a heads.
That's so weird. Is that because before you mentioned
It's not intuitive initially. Probabilities are that way. That's why we do them.
like people like at a roulette table, like expecting black to come up after a bunch of reds?
Right, that's very different.
How is that different?
How is that different? So that is, I know that it went black, red, black, 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 whatever. Now I'm saying where are the odds that the next one is a red? The odds that the next one are a red, it doesn't care what came before.
Is that not the same as what we just
Just like when you were up here, where are the odds that the last flip was a tails, given that, or sorry, what are the odds that the first flip was a heads, given that the last flip was a tails? That doesn't change anything. Now, if I were instead looking at these and I say, I've spun my roulette table 6 times, I tell you that it came up, how many times did it come up black? 5 of those. It came up 5 of those times. What are the odds that the first position was a black?
Oh, very high.
And it's a completely different question.
That's a way different question.
Okay.
Weird.
So, people crossing those questions in their head back and forth, confusing independent and dependent events, trick themselves into thinking they can go win at Vegas. Not going to win. Or at least it's not likely that you're going to win. But if you all go play at Vegas, someone will win. Odds are at least one of you will win. Right? Okay. Next one. Definition now of conditional or of events being independent. So let A and B be events in our sample space S and P. Then A and B are independent events if and only if the probability of A intersected with the probability of B. The probability of getting A and B is just the probability of A times the probability of B. Let me connect this with your intuition. What's the probability of getting heads on my first coin flip?
50%.
What's the odds of getting heads on my second coin flip? And so what's the odds of getting heads on my first flip and my second flip? 1/4. And you just multiply them together. That's what this is saying. The probability of getting heads on the first and heads on the second is just the probability of heads on the first times the probability of heads on the second. That's what it is when they're independent events. Another way to think about it, here's the way I personally like to think about it. Two events, A and B, are independent if the probability of A given B occurred is still just the probability of A.
That makes a lot of sense.
So this is the way I like to think about it. Here's its exact definition. Let me show you how this gives you this.
Sweet.
Okay? And then you can think about it whichever way you want. And it's just a quick scribble. Scribble this out. We already know, always and forever, this equation, right? Oh, sorry. Take our definition of conditional probability. Our definition of conditional probability is the probability of A given B is equal to the probability of A intersect B over the probability of B, right?
Yep.
Just by definition. Now, if the two events are independent, then the probability of A intersect B is just equal to this. That's what it means for them to be independent.
Oh, that makes sense now.
Yeah, so this is just the probability of A times the probability of B over the probability of B. And now cancel out probability of B, top and bottom, gives you the probability of A. So if the events are independent, then the probability of A given B will just be equal to the probability of A. Similarly, the probability of B given A, if you plug it in, will still just be the probability of B. Make sense? Okay. Just some notation to save you from having to write massive sample spaces. So let S and P be a sample space, and let N be any positive integer. 1, 2, 3, 5, whatever. And let S of N be the set of all length N lists of S. Or in other words, S of N is S cross S cross S cross S N times. Then we call S to the N together with P. We call it the n-fold repeated trial sample space of S and P, where the probability of S1, S2, Sn is just equal to the product of all their individual probabilities. Okay, that is a mouthful, but this is very simple and something we've already loosely been using. So, let's give a concrete example, writing it out explicitly, and then go over that again, and it'll make perfect sense.
Okay.
So let's say S is rolling a 6-sided die, so we can get 1, 2, 3, 4, 5, 6, where the probability of each outcome, little s, is just equal to 1/6. With me so far?
Yeah.
Now say I want to roll 2 dice instead. I don't want to write out a new sample space. So, what we could do is just piggyback on this space and say when we're rolling 2 dice, we're just now going to use S2, which is going to be S cross S, this cross with itself, which is exactly what we expect. What's S cross S? That's 1, 1. It's everything in this element paired with everything in the set again. 1, 2, 1, 3, all the way down to 6, 6. So that's what S to the 2 would be. And now, what is our probability now of 1, 1? If we use this definition, the probability of your ordered list, first thing, second thing, if you only have 2, is just the product of their probabilities using your previous probability function.
136.
So what's the probability of 1, 1? That is the probability of 1 times the probability of 1 using this probability function, which is 1/36. Or what's the probability that you got a 5 then a 2? Well, that's just equal to the probability of a 5 times the probability of a 2, which is equal to 1/6 times 1/6 is 1/36. So this is just a way to define your sample space once that you want to use, like your sample space for 1 die, and then just use it for if you're going to be rolling 2 die,
It's kind of like
or if you're going to be rolling 3 die, or 4 die, or 5 die, or 100 die.
kind of like a basis element almost?
Kind of.
Okay.
So it's just a way to quickly construct new sample spaces from existing sample spaces rather than having to redefine them from scratch every time.
Right.
And it can save you some headache.
That's nice. Could you do it? Can you define a sample space to be the cross product of two sets that aren't the same set? I mean, yeah.
You can.
Yeah.
You can define a sample space however you want. It's just understood. If you already have some sample space defined on one die, then now I can quickly talk about ruling 4 die. It's just understood this is what it is, and so you don't have to redefine everything.
Why is it called the trial sample space?
Because, so the n-fold repeated trial, n being how many times I'm going to be rolling the dice, rolling 4 die is logically equivalent to repeatedly rolling 1 die 4 times. So 4-fold repeated trial. Repeat it over and over again 4 times with your same sample space.
Gotcha. Sweet.
And then what's the probability of your first roll being a 6, your second roll being a 6, and your third roll being a 6? Well, the probability 1 6 times 1 6 times 1 6, etc. And then if this scares you, don't look at it, but for those of you who want the dense way of writing it out, there's a dense way of writing it out.
What a pi.
Your product. Yeah, remember. Pi for your products, sigma for your sums.
Yep.
The product from k goes 1 to n of each of your s of k's. That's your probability of some particular outcome. But you just multiply them together the same way we've been doing.
Is there also a notation for repeated exponentiation?
I don't know.
Like
I've
2
never
to the-
used it if there is.
2 to the 2 to the 2
But
to the
there probably is. As you get into niche fields, like I forget a bunch of the special notation I knew for different things, but they have their different special notations. The way that they put the number, sometimes parentheses there. There's a bunch of them. Okay, anyways, so there we go. That's all that is meant by a n-fold repeated trial sample space. Sounds like a mouthful, but very straightforward. So now if I have my sample space here for, oh shoot, there's a definition there. I've got my sample space here for rolling 1 die. Let's really quick look at S sub, I don't know, we'll just do 3. So S sub 3, what does this look like then? It could have something 1 1 1. 1 1 2, all the way up to 6 6 6. Right?
Yeah.
And now, what is the probability of one of these particular rolls? So let's say, what's the probability of getting a 1, then a 5, then a 3?
It's 1 and 2.
By definition, just following that,
Yeah.
of a 1, a 5, and a 3, it's the probability of the 1 times the probability of the 5 times the probability of the 3. So that's equal to the probability in our initial sample space of getting a 1 times the probability in our initial sample space of getting a 5 times the probability in our initial sample space of getting a 3, which in our case is just 1 6 times 1 6 times 1 6, which is equal to,
1 over 260.
okay,
If they're all the same probability, can't you also just say it as 1 6 cubed?
you can, but here's just how you do it in general,
Right.
because they could have different probabilities.
Can my calculator run the repeated multiplication?
I'm sure that there's a way that you could plug in product notation. Okay. I guess I had an example right here written up. So let's do this example. Let SP, where S is 1, 2, 3, 4, 5, 6, and the probability of each one is 1 6. So just rolling a single fair die. So if we consider S sub 2P, once again, what would S sub 2 be in this case?
Just S cross S.
1 1, 1 2. Not gonna write them all the way down to 6 6. So we already did that one. And then what's the probability of 1 1?
136.
Well, that's the probability of 1 times the probability of 1, which in this special case comes out to 1 over 36, or 1 6 times 1 6. Since the probability of any outcome was 1 6, which is equal to 1 over 36. Okay. Let's look at tossing an unfair coin. So my sample space, flipping a coin, could be heads or tails.
Right.
We're going to say that the probability of heads is some number p.
Okay.
Could be like 60%, could be like 30%. We're no longer going to assume it's just exactly 50%.
Okay.
Question, what's the probability of tails then?
Oh.
If my probability of, let's pretend p was 60%. If my probability of heads was 60%, what's my probability of tails?
Oh, 40. So it's just
40%.
Just
1
1
minus
minus p.
1 minus p.
We did that before.
Okay, so now let's upgrade and let's say that we're now in S5, where this is our sample space. You with me? So now what's the probability of heads, heads, tails, heads, heads? Well, what's the probability of heads? P. Times, what's the probability of heads? P. Times, what's the probability of tails? 1 minus P times the probability of heads times the probability of heads. P. Which is equal to just P to the 4 times 1 minus P. That's a 4, not 9.
Can you simplify that out?
That's as good as you're going to get it. That's perfectly factored.
Okay.
Okay, now what's the probability of heads, tails, heads, 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 heads?
It's the same thing, isn't it?
Yeah, it's the exact same thing. So it's just going to be P to the 4 times 1 minus P. Good?
Yeah.
Okay. And with that, we get to our last problem and one of the fun problems to talk about. So, a game show that they used to have back in the day, hosted by a guy by the name of Monty Hall. Here's the way that the game worked. There were 3 doors. We'll call this door 1, door 2, door 3. What he would do is he would hide a car behind one of the doors. So one door gets a car behind it. An actual car for the person, big winner. And then 2 of them have a goat. So, got our goat. You guys get to see some insane drawing. And we got a goat. I didn't do as much practicing during math classes, so. Okay. Now here's the way that Monty Hall will play the game. All the doors are closed. You can't see what's behind them. You get to choose one of the doors, any one of the doors. Say you choose this one. What Monty Hall would then do is he would open one of the doors that had a goat behind it and say, number 3 has a goat behind it.
Do you want to switch?
Do you want to switch or keep your choice?
Okay.
And the question is, should we switch or should we keep our choice? Or does it matter?
It matters. I don't know the math behind it, but it does.
You know
It matters?
I think so.
So which way? Do we want to switch or do we want to keep?
Switch.
We want to switch and that's going to help us?
Ah, shit.
Statistically,
Or is it the same?
It feels like it
I
should be
think
the
it's
same, but I don't think it is.
slightly. I think it helps by a small amount. I don't know.
Helps by a small amount. Seems like it should be basically the same.
Well, let's figure it out.
Should we figure it out?
Yeah, let's do it.
Now, most people would think that Monty Hall was trying to trick them into switching. So they would keep it the same. But, yes, you should always switch. Now, to see why you should always switch, it's easiest to just play the game.
Okay.
So, who's going to play the game with me?
Me.
Alright, you're going to play the game. And you have to stick to the strategy of either always not switching or always switching. Doesn't matter which way we go. Let's start with you never get a switch. See what happens. I need you to write the numbers 1, 2, 3 randomly down your sheet of paper. Just random. 1, 1, 2, 3, 3, 2, 1, 1, 3. Pick random numbers. Just start writing them down. Yeah, you're hiding our car for us. I, as Monty Hall, can't know where the car is.
Okay.
I might trick him into picking something. 1, 2, or 3. You got some random numbers for us?
Yeah.
Alright, so it starts out with, you make your choice. What do you choose?
2.
He chooses 2. Now you need to tell me one of the doors that he didn't choose that has a goat behind it. Maybe he chose one with a goat, maybe he didn't. But for sure, either 1 or 3 has a goat behind it. So tell me where a goat is.
1.
1. So there's a goat here. He's going to stick to the strategy of always picking the same one.
Okay.
Right? Did you win? Did he win? Was it 2?
Like, okay, how am I?
Oh,
doing
we'll
this?
set the game up again.
Okay.
And we'll say that you always stay the same and I always switch. So we can always see who wins, who loses. And we'll keep the scoreboard.
Alright.
And we're going to set it that way so I can win. Alright, well, we're going to do Donnie versus Stanley. We'll see who wins. So your numbers that you are writing down is where the car is.
Okay.
So if you wrote 2,
Oh.
that means that there's a car behind door number 2, a goat behind door number 1, and a goat behind door number 3.
So it's just.
If you chose 3, then that's where the car is, and there's goats behind these doors.
Okay.
So I just write some random numbers and then choose one?
You just write some random numbers. So your first number, if your first number is a 2, then that means for our first game, there's a card behind door 2.
Oh, okay.
You ready? All right, we got our random number generator
Okay.
ready. We're ready to start playing the game. Okay. So once again, pick a door, any door.
1.
He picks door number 1. You're going to tell him that there's a goat either behind door 2 or door 3. One of them for sure has a goat. Which one has a goat?
2.
2 for sure has a goat. I'm going to switch now, so I get door 3, he gets door 1. Who won?
Stanley.
Stanley won. Oh, shoot. Playing again. Pick a door, any door.
3.
3. One of these has a goat.
2.
I'll take door 1. Who wins?
He does.
You won again. Stanley's reading your mind. So we'll go again. Pick a door, any door.
3.
3. One of them has a goat.
1.
So I take door number 2. Who wins?
You do.
I do. Play again. Pick a door.
3.
3. One of them has a goat.
2.
2. So I take door number 1.
You.
I win. And you're going to notice, either I win or he wins every single time.
Right.
The only way he wins is if he gets it right on the first try,
Which is a 1/3 chance.
which is a 1/3 chance. If I win every time he doesn't win, how often do I get a win?
2/3.
2/3. And so that's what should start approaching the more we play the game. Let's keep playing the game.
Gross.
Pick your door.
2.
2. Did you get it right? It's behind door 2?
Yeah.
So I don't win. Next, pick a door.
2.
Did he get it right?
Yeah.
Stanley's good at this game. I mean, kill, even with great odds. All right, pick a door.
3.
3. Did he get it? I'm coming back. And you see how me switching and him staying the same, I'm going to win twice as often as him playing the odds.
But once you've made your choice,
I'm always switching. So if it wasn't behind the door that he chose, I win. If it was behind the door that he chose, he won. Now let's think it through a little bit more. So this time we'll write down numbers as we go. Once again, Stanley, pick one.
3.
3. So right now, there is a 1 in 3 chance it's behind this door. And a 2 in 3 chance is behind one of these doors, right?
yeah.
She tells us that there's a goat behind
2.
2. So now there's a 2/3 chance. There's a 2/3 chance that's behind one of these doors.
You know it's not 2.
And now I know it's not 2. So now there's a 2/3 chance it's a 1. And what was it? A 1.
That's so weird. That's so weird. What? I hate that.
And so, let's go one more time. Pick a door.
2.
Was it 2?
It was 2.
Stanley's winning. All right. Playing on human psychology,
Yeah.
because a person's picking the numbers rather than a random number generator, but it's fine. So that's the way the game goes. Although our experiment isn't showing it, does everyone understand the math?
Yeah.
And why, if we keep going long enough, odds are I'm going to end up winning the game. Good. One more thing we could talk about. I don't know if I talk about it this time or next time. It's kind of related to someone coming up with random numbers. Human beings, when we come up with random numbers, we tend to not cluster numbers together.
Yeah.
When eventually you're going to get a cluster of numbers. And so, the famous story of a probability professor, he would say, I want you guys to go home, I want you to flip a coin 100 times. And write down heads, tails, whatever it comes out to. He says, and I don't care if you make it up, or if you actually go flip the coin. But when we're done, I'll tell you which of you actually flipped the coin versus which of you made it up. And there was some special number, I can't remember, but it was something like 6 was the magic number, where you would expect that 6 heads or 6 tails would have showed up in a row in 100 flips. Somewhere along there would have been that many in a row. And so he would just go check to see if there was that number in a row. A person coming up with random numbers doesn't want to put 6 heads in a row. That doesn't feel random. They got to switch it up more. So the people that made it up would never do that. People that went and flipped it in general would do that. And so the majority of the time he could tell you whether or not you actually carried out the experiment.
Interesting.
So, just interesting for that point. Okay, so that's the end of today's lecture. Probabilities, diving in a little bit more. We still got 2 more weeks on probability, so long time before your test. Enjoy that, celebrate. Any questions before we end today's lecture?
It feels like when we get into conditional probability, we should, like, if you're trying to set up some kind of function in terms of another probability, I feel like it's like a differential equation almost, doesn't it?
Not a differential equation, but just looking at this picture for a second, you can see how calculus could quickly start coming into the picture.
Yeah.
Because in general, how do we calculate a probability? A pictorial way of thinking about it, it's some area divided by some other area.
Right.
And so, when it's perfect square areas, then okay, anyone can work with it. But now, once you start having the area bound by some function, right? If I say something, just make up something stupid. We got some parabola right here. I say I throw a dart into this corner. What's the odds it came under that parabola? Now that's already something that majority of students can't do.
Right.
Because
You need the calculus for that.
you need the calculus for that, and that's just some simple scenario like this. So when you start dealing more and more with real-world phenomena, where you're mapping it with some function, then yeah, you have to use calculus to calculate the probability. And now when you start dealing with functions, probability functions that are related to more than one variable, now you have to start working in multiple dimensions.
And that seems like a problem that would be pretty common in the real world.
Right, very normal thing. And so then you need multivariable calculus. And it doesn't necessarily mean that's hard. It's just tracking multiple variables. You're going to be dealing with some sort of a hyperspace, whatever you want to call it.
Right.
And so yeah, ratios of volumes, ratios of integrals is how a lot of probabilities are calculated. But even just limiting ourselves to discrete math, it's a bit surprising how much we can do and how useful it can be getting the intuition early on. Because all the formulas you get when you go through probabilities and statistics discretely, we're not going to go into a very deep dive of it, but it's shocking how often you just go and you replace all your sigmas with integrals, and it just translates right over to the continuous case.
Makes sense.
Right, because the integral just a limit on its own. Anyways, we won't be really going into much of that, but there it is. I guess we will a little bit, like when we calculate expected value, stuff like that. Any other questions? All right. I need your guys' tests.